Hello Internet! I'm wearing my almost period correct jacket today because in this video we are going to challenge the C64 to do something quite special.
I'd like to tempt you to take part in an experiment.
But first, have you watched these wonderful videos by Perifractic? If not, then you should do that right now, because this video is kind of a follow-up to them. In 1985, four computer geeks on British television challenged themselves and their viewers to an experiment.
It may seem a crazy idea.
They wanted to see if you can transmit program code for a microcomputer by encoding it in a blinking dot on the television screen. Viewers got some instructions in advance to build a circuit.
It'll probably blow up. Quite harmless though.
That uses a phototransistor to sample the screen and transmit data to the user board of their microcontroller. They also got a receiver program to type in that should capture this data and store it in the memory of the computer. Unfortunately, I have never heard of anybody who completed this experiment successfully. But this made me curious. Could it work in principle? I think it might, because the ideas behind the circuit and the computer program are sound. Maybe it just needs a couple of small fixes. And we could make it work. So let's try. There is quite a lot to this experiment.
Let's spare a couple of hours.
So this video will be a long one. Just use the video chapters below if you happen to be impatient. Few things are better than receiving new parts for a project. And here they are. Phototransistors, multivibrators, and of course the all-important sucker.
You'll need to build a receiver like this.
Let's see whether we've got everything to build the original circuit. We've got the 74 LS123 multivibrator.
It's a bit of a mouthful, that.
The BC108 transistor. This transistor is available in multiple binnings. I chose the BC108C, which has the highest amplification among them. The particular phototransistors given in the original component list are the only components not readily available today. Since I do not think that the choice of phototransistor is crucial, as long as it is sensitive to visible light, I chose the Vishay BPW96C, which is easily available and has decent sensitivity. With a 470 kilo ohm potentiometer, a 6.8 microfarad tantalum cap, and a few resistors, our list is almost complete. We just need a 9 volts battery clip and battery, a protoboard and some hookup wire, and we are ready to go. But what about those mystery components? The layout suggested in the magazine article back then didn't really work for me, so I decided to sit down with the pinout of the multivibrator and create my own board layout. While I'm building the circuit, let's briefly talk about how it is supposed to work. The basic idea is simple enough. In order to transmit a character like A, for example, the numerical value corresponding to this character will be sent bit by turning the dot on the TV bright for a 1 bit and dark for a 0 bit. European TVs of the time refreshed with a frequency of 50 Hz, so the fastest bit time we can achieve this way is 20 milliseconds per bit. The timing of the bits is fixed this way, but the receiver still needs to know when the transmission of a byte starts. For such serial communication, there is a standard way of achieving this that is also used in this experiment. Before the transmission of each byte, a low start bit is sent, and after the transmission of the byte, one or more high-level stop bits are transmitted. This means that exactly 20 milliseconds before the transmission of the byte begins, there will be a high to low transition of the signal. This transition is guaranteed because in contrast to the varying data bits within the byte, the start and stop bits always have the same values. Therefore, the receiver can simply wait for this high to low transition, then wait for half a bit time, and then start sampling the signal every 20 milliseconds. In this way, ideally, each bit will be sampled exactly halfway throughout its period. This approach of sampling each bit in the middle of the period gives the receiver the maximum amount of margin for timing errors. Synchronization is then repeated with the falling edge of the following byte, meaning that the precise bit timing has to be kept only for about 9 bit periods. So far, so good. The C64 should be able to keep this 20 millisecond timing easily. However, there is a complication related to how CRT television screens work. We will never get a nice brightness signal like this one by sampling a CRT television with a phototransistor, because the TV image is created by an electron beam that scans the image area sequentially, and only for a very short time the electron beam will pass the sensitive area of our phototransistor. So we will only ever see very narrow and probably irregular pulses of brightness whenever the electron beam crosses the sensor area. The computer could not sample this signal reliably. Therefore, our circuit needs to do some work to clean up this signal to make it look more like this regularly shaped idealized signal. This is what the multivibrator in the circuit is used for. Whenever the brightness detected by the phototransistor rises sharply, the multivibrator is triggered and will produce a high level at the output for about 20 milliseconds, independent of how quickly the original brightness pulse goes away. If the pulse length of the multivibrator is tuned correctly, it can create an almost ideal signal. The pulse width must be long enough to generate high levels that last at least 20 milliseconds each, and if there are bright pulses with a distance of 20 milliseconds, we want to see a continuous high level at the output without any dips in between. On the other hand, the output pulses must not be much longer than the nominal 20 milliseconds, because otherwise, if you have a 1 bit followed by a 0 bit, the high level would be prolonged too much and it would interfere with a reliable detection of the low level for the 0 bit. For the sensor assembly, I drilled a 4.5 mm hole into the suction cup to securely hold the phototransistor. I first tried to use the original clip to plug the hole, but the phototransistor would protrude too far into the cup. I found that the cap of one of these crappy stabilo pens would make for a perfect sensor housing. I soldered a twisted pair of wire to the phototransistor and secured it with some heat shrink. To make the suction cup airtight again, I filled it with some bathroom silicone. And that's the sucker completed. Since nobody so far has gotten this circuit to work, I think we should first test it and see if it is at all functional. And for that we will allow ourselves the luxury of some modest test equipment. I'm sure you could do all of this with period correct gear also, but I don't have enough of that. For simulating the TV screen, I have built this test fixture that contains a white and a red LED. Currently the white one is used, and the function generator makes this LED blink with a frequency of 50 Hz, and it is lit only for a very short time. The output of the function generator also goes directly to the scope, to channel 2, which is shown here in cyan, so we can trigger synchronously to the light pulses. So let's try it. I try to put the sensor exactly over the LED. And indeed we see a pulse train now coming out of the data output of the circuit. And I have calibrated it almost correctly. We see that the pulses coming out of the circuit are somewhat shorter than 20 milliseconds. I will now turn the potentiometer in order to adjust the pulse width of the circuit. You see it is somewhat adjustable, but we immediately notice the first problem, that it is extremely fiddly. So just by tweaking this potentiometer the tiniest amount, the pulse width changes quite a lot. I realized I did a really poor job of demonstrating how fiddly this adjustment is, because on the camera it's not at all obvious how tiny the movements are I make on the potentiometer. I have therefore prepared a visualization of the adjustment range. Here we are using the formula from the datasheet to calculate the pulse width, and with the 470 kilo ohm potentiometer we get an adjustment range from 6 milliseconds to 1061 milliseconds, so to over a second of pulse width. Now we need to adjust the pulse width with a tolerance of about plus minus 5 milliseconds, and that's being really generous. When we visualize the whole range of the potentiometer as a 10 centimeter line, the target range we need to hit is less than a millimeter in width. We need to hit a smaller than 1% range, and it is also right near the start of the potentiometer, where potentiometers tend to be even more fiddly. 470 kilo ohms is way too large. A range of 10 kilo ohms should be sufficient, so this is too large by almost a factor of 50. It is very strange because for the BBC Micro, which of course also expects 20 millisecond pulses, they specified this potentiometer with 22 kilo ohms, which is a much more reasonable value. I took the 470 k ohm potentiometer out and replaced it by a 10 k ohm, and now the adjustment is much smoother and the range is just so that we can make the pulses somewhat longer than 20 milliseconds. This is working much better now, and I think the circuit is now fully functional. We seem to have a functioning receiver, but what is it going to receive? As you may know from Perifractic's videos, the recordings of the original transmissions that are available online do not have sufficient video quality to make a reception feasible. And the better quality master tapes cannot be shared due to copyright restrictions. So we will have to make our own transmission based on the program data that Perifractic and the C64 crew decoded. Now, one of the simplest ways to convert this program data into a video transmission would be to use the C64 itself, because the VIC2 chip in the C64 already knows how to generate a good PAL signal. However, putting the program from the past into the C64 first and then receiving it back just does not seem like the right thing to do. We want to have a proper transmission. Therefore, my plan is to generate the video signal using my function generator and an Arduino Nano microcontroller. In order to convert the data that we want to send into a serial transmission, I wrote a little Python script that adds the required start and stop bits. It also creates this visualization of the whole transmission, showing each bit as a little square. Keep in mind that every one of these about 12,000 bits needs to be transmitted correctly in order to receive the program from the past. It's time to test the circuit with a real signal sampled from a CRT. But the problem is, if I use my trusty 1084S as the TV stand-in, what do I connect my C64 to? Would be good to have another monitor. Maybe I should have finished the restoration of this cute 1404 years ago. I got the monitor working, but using the 1404 was not one of my brightest ideas. Literally. When I tested the circuit with the 1404, I got a total flatline at the output. It did not work at all. Well, I found a workaround that brought it to life. After taking some measurements of the phototransistor current, I was a bit wiser and I had learned quite a bit about both the 1404 and our receiver circuit. The 1404 turns out to be objectively very dim, which surprised me because it looks just fine to the human eye. This is probably related to the amber phosphor of the 1404 having a much longer afterglow than that of a TV or color monitor. I found a way to make the receiver circuit adjustable to a wide range of monitor brightness. I replaced the fixed resistive divider at the base of the transistor with this adjustable setup. This is likely unnecessary if you are using a regular TV or something like a 1084 color monitor. It seems I just picked the worst possible test case. Oh well. Curiously, the 470k ohm potentiometer is just the right size for this purpose. It really makes me wonder whether this wrongly specified 470k that makes no sense for the timing adjustment was really meant for something else and there was some kind of miscommunication in the original design team. Nevertheless, through this detour, I gained a few insights regarding the design of the receiver circuit. I also added a jumper so we can optionally supply this power rail that is originally meant to be 9 volts from the 5 volt supply. The jumper is currently set and I'm supplying the whole circuit with 5 volts to both of the power rails. From the beginning I wondered why the designers chose to have this external 9 volt battery supply in addition to the 5 volt supply coming from the computer. Through our measurements we now learned that the 9 volts is not there to get a larger signal from the phototransistor. The amount of current drawn by the phototransistor hardly depends on this supply voltage at all, at least within a reasonable range. With a given amount of photons received, the transistor simply cannot conduct more current than it does. Therefore, I suspect that the 9 volt battery supply was chosen for this supply rail in order to make it noise-free, because it supplies a high impedance part of the circuit that could be susceptible to noise coming from the computer power supply. I wonder whether we can achieve the same effect by filtering the 5 volt power supply in order to supply this rail. This would allow us to get rid of the ugly external 9 volt supply, and we could also omit this resistor, the only purpose of which is to make sure that the trigger signal at this node stays at a maximum of 5 volts. But wait, you might be saying, what's with all that aluminum foil? Well, right now it's doing nothing, but let me show you something. The dot is now set to be permanently bright, and on the scope we see the output of the BC108 transistor at its collector. This is the trigger signal going to the multivibrator. We do have quite a strong signal, which is good, but let me zoom in a bit. If we zoom in further, we see that this noise is not at all random. It has a very particular frequency that coincides with the horizontal frequency of the monitor. The electromagnetic fields that are alternating during the horizontal deflection of the electron beam are coupling to this cable to our phototransistor. But watch what happens when I connect the aluminum foil around the cable to circuit ground using this jumper wire. I made some screenshots for you because I'm not sure whether on the camera you can see the full extent to how much the signal is changing. And it works great even though the real part of the cable is not shielded at all. So we know that all this noise is coupled in probably in the first few centimeters of the cable. I should have used a shielded coax cable right from the beginning. Here is how I later built a much nicer sensor assembly using some old microphone wire. This version has shielding up to the first few millimeters of the phototransistor, and it gives an even cleaner signal. I now have the dot on the alternating sequence, and the scope is showing the output of the circuit in cyan. And we can see that the multivibrator does a nice job of cleaning up this irregular brightness signal to an almost perfect square wave signal. And this is the permanently bright dot, and indeed we see that we don't have any dips and the logic probe is not showing any activity. I've set up things now so we can test our sensor with another monitor, namely with the Commodore 1084S color monitor. The circuit will still be powered by my bench supply, since I hesitate to switch to the computer power supply until everything is working fine as it is. However, we will connect ground and the data output to the user port of the C64 using this user port breakout adapter. Let me insert this adapter in the C64 user port and turn the machine on. We have the bright dot here that is permanently on, so let's put our sensor over this dot. And would you look at this? Oh my god, it works so much better than with the Commodore 1404 Amber monitor. The first one is a test sequence that varies the downtime of the signal but has always the same uptime of 1 bit. The idea here is to test that the positive pulse width should not depend on how long the signal has been low before. And zooming into the sequence, it just looks absolutely perfect. So let's try the next test sequence. This is the opposite. It has varying uptimes of the signal and in between always a downtime of exactly 1 bit. And again, we should see that the length of the, in this case, negative pulse does not depend on how long the signal has been high before. And again, this just looks perfect to me, so I think we are ready to go on to the next step and power the circuit from the computer. The bench power supply is gone, and I have now connected the plus 5 volts line to the plus 5 volts of the user port adapter. I'm currently testing the resistance between plus 5 volt and ground to make sure that we do not have any short here that we then present to the user port that could damage the C64. It looks fine. 2.8 kilo ohms. Will we see any worse behavior with the power coming from the computer? Let's see. Fingers crossed, let's turn the thing on. At least the computer is alive. So let's again load the tuning program. The circuit seems to work just fine. And let's try the test sequences. At least on the scope I do not see any obvious degradation of the signals. Now this is awesome. It means that even without adding any additional filtering to the circuit, it should be just fine to power it from the computer like that. No need for this ugly 9-volt battery connection. We do have a little change of plans. Originally I intended to use the 1404 as a TV stand-in, but now we found that it has quite different characteristics than other monitors and TVs. Furthermore, I found out that we still have a video recorder at home, and this opens up an interesting possibility. The new plan is now to generate the blinking dot signal using the Arduino, to record it on VHS tape, and to then play it back and go from the RF output of the video recorder into an actual TV. This way we have the most realistic reproduction of the TV signal that people would have had back then. Our setup for generating and recording the transmission signal is ready. The function generator generates a combination of vertical and horizontal sync on channel 1 and a pulse for horizontally locating the blinking dot on channel 2. These signals are combined in the circuit I built for this purpose with an enable signal coming from the Arduino Nano. This enable signal tells the circuit when to show the bright dot, and it contains the serially encoded program data. Explaining the details of this circuit would make the video too long, but if anybody is interested in that, please tell me in the comments and I can share more about that. The output of the combiner circuit goes to the input of the video recorder, and from the output of the recorder it goes to the monitor so we can visually check the signal. I will now press the record button. Pressing the Arduino button should activate the 1 Hz blinking sequence first. Let's record a few seconds of that. Next we will record the alternating sequence for a few seconds for debugging purposes. Now let's turn the dot permanently on. So let's go. A few seconds of brightness and then you will see the actual data transmission. Here it goes, the magical blinking dot. The transmission should last for about 4 minutes. I timed the original transmission, and from that I calculated that probably the original used 3 stop bits per byte. So that's the same that I'm doing here on the Arduino Nano. It's done. The dot has gone dark. The transmission sequence is finished. Let's stop the recording. Okay, the tape has rewound. Let me disconnect the output of this circuit. Now we are sure that no signal is going into the video recorder, so whatever we see is coming from the tape. Let's play it. And there's our 1 Hz blinking dot. That looks good. The alternating sequence. And here tracking problems rear their ugly head. For some reason they were particularly bad when the video recorder was playing back its own recordings. I fiddled with the video recorder for hours, and after many attempts I finally had a recording that played back reliably enough. The moment of truth is getting closer. I have the C64 connected to its monitor and also to the TV through RF. So let's run the tuning program. The tuning program published for this experiment was meant to help the user adjust the pulse width just long enough that for a permanently bright dot, no low levels appear on the user port. The program is very simple. It just samples the user port repeatedly, and if at any time it detects a low-level signal, it puts an asterisk on the screen that remains until it is cleared by pressing a key. We have the dot on the TV, so let me place the sensor as accurately as I can. We will use a somewhat modified tuning procedure to set up our 2 adjustments for sensitivity and pulse length. Let's first find out which range of sensitivity we need in order to trigger the circuit. We will first turn the circuit to minimum sensitivity and the pulse length to maximum. So currently the C64 is not getting any high signals, therefore the asterisk is all the time showing. We will now turn up the sensitivity until we can make the asterisk go away. With the sensitivity set to about 9 o'clock, I could for the first time make the asterisk go away. Now let's do it from the other side. We set sensitivity to maximum and the pulse width to minimum. And we see that even turning up the sensitivity to the maximum, we still get low levels with the minimum pulse duration, so there is no harm in turning the sensitivity up quite a bit. So let's choose a compromise setting in the middle. Go back to maximum pulse length. The asterisk is gone. And now I reduce the pulse length slowly until the asterisk reappears. There we have it. So now our pulse width is just slightly too short. I will now periodically press a key and increase the pulse width until the asterisk stays cleared. And there it is. It should now remain cleared. So far this is looking fine. Let's just add a little bit of additional pulse width to have some margin of error. Now hopefully our circuit is tuned correctly. We could check with the scope, but that would be kind of cheating, right? So let's try it like this. At this point we need to talk about the receiver program a bit. Right after I had seen the first video by Perifractic, I disassembled and analyzed the published receiver program in order to understand how this experiment was supposed to work. Doing that, I found that the published program was missing a crucial piece, the part that is supposed to store the received bytes into memory. Confusingly, only the C64 receiver program had this problem, while the program published for the BBC Micro was complete. Exchanging a few YouTube comments, I learned that users on the Lemon64 forums had already discovered these facts, and a user going by the nickname MC513 had already published a completed receiver program for the C64. That is the program we are going to use in the following, because with the program as it was originally published, you would never get the experiment to work. The receiver program should be active now, so let's find the beginning of the transmission on the tape. There it is, the beginning of the transmission with the permanently on dot. I will now place the sensor above the dot and then press a key to start the receiver program. So now all we can do is wait. Oh no, we are having some glitches on the screen. That's really bad because there's no room for error. This receiver software has no kind of error correction whatsoever. So if there's any glitch that is recognized by the sensor, the program is corrupted. We are getting a lot of glitches now, and I think it's too much. Wow, the program exited at about the right time, somewhat above 4 minutes into the transmission. So we have some chance of having received something. Let me now save the received program. Okay, we got an out of memory error. Strange. Let's try listing. Is there something there? Wow, there's a program there. Okay, let's just try to run this program because it looks like we got something. Oh no! It started the banner, but then there is a syntax error, probably because of the glitches. Our program is corrupted. Anyway, it was really encouraging that we got the program at least partially correct into memory. So let's just try again and hope that the glitches aren't as bad this time. I have reset the C64 and loaded the receiver program. Let's start it. Let's start the playback. And I will put the sensor on the screen. And press a key. Now let's wait again. Do unfortunately get a lot of glitches again around 3 minutes into the transmission. The receiver exited. So let's see what we got. Saving just doesn't work, unfortunately. Listing looks similar to the first time we tried. Woo! It's working! At least this part of the program is working. Look at that! Press spacebar when ready. Will it work? Will the rest of the program work? A mathematical square. Please type a number between 1 and 100 and press return. Of course, we have to type 42. And we got our magical square. Do you want to try another number? Yes. Let's try 3. Okay, this one I think I can check it in my head and looks right. But not very exciting. No. Okay, that was the program from the past. And we actually received it from this tiny television from the past, built in 1968. Amazing. It's just a pity that I cannot save the program. Does it work now? Woo! I think we have it on disk, or rather disk image. The problems we had with saving earlier are probably due to the state of the BASIC interpreter being messed up after the program is injected into memory. It seems to repair itself after running the program. Now that the program is saved, we can also compare it to the original data we sent. And it turns out to be identical bit for bit. Our reception was 100% successful. Now, one thing I'm really curious about is how good our tuning was that we achieved using this improvised tuning sequence. So I connected the output of the circuit to the scope. Here it is, the alternating sequence. And would you look at that? What kind of pulse width do we have? 20.6 milliseconds. That's just perfect. There it is. This is what the transmission looked like to the C64, and it looks like a perfect digital serial signal. So yes, the circuit from back then absolutely works if you do the small but crucial modification that we made. So what can we say with hindsight, looking back to 1985? I think the original experiment would have had a fair chance of success if it wasn't for the two showstoppers we found. The C64 receiver program was missing a crucial part, and the wrongly specified potentiometer would have made it almost impossible to tune the circuit correctly. It's strange that both of these problems affected only the C64 version of the experiment, and I wonder whether BBC Micro users had better luck with their reception attempts back then. With these two fixes in place, it all seems doable, given a good TV signal and a bit of luck. The other changes I made are optional. Having the sensitivity adjustment is nice, and shielding the sensor is certainly a good idea, but I think neither is strictly necessary if you have a decently bright CRT to work with. I also wrote a much improved version of the tuning program that actually measures the pulse width and gives you immediate visual feedback about it. This works so well that it actually allowed me to discover a minor instability in the original circuit that caused unwanted variation in pulse width. Adding a 10 nanofarad capacitor resolves this instability, but I think also that is not strictly necessary for getting a successful reception. Despite its imperfections, it was a very fun and inspiring project that 4 computer buffs came up with back in 1985, and they deserve a round of applause. There's just one thing I can barely forgive them. Breaking the first law of hobby electronics, their circuit design did not include the 555 timer. You might say that the 555 timer does not re-trigger, which is true, but I found a way to hook two 555s together in a way that just works perfectly for our purpose. The resulting circuit is even simpler than the original one in that it does not require the additional transistor. One could make an endless list of modifications and improvements to this project, but I need to finish this video. Getting all of this to work already took a lot of blood, sweat and tears. Big thanks to Perifractic for reminding all of us about this wonderful episode in microcomputer history. To user NC513 on Lemon 64 for providing the completed receiver program, and to my friend Ernst for borrowing me this cute TV. For more details, contact me in the comments and take a look at the GitHub repo linked in the description. Thanks for watching.
And until next week from the 4 Computer Buffs team, it's goodbye.